Okay, so what is it, 7.4? 7.4, doing some homework here. So we're talking about logarithms, and question number 1 talks about this diagram on the left in your textbook there. And it says, for this diagram on the left, this function, state the x-intercept, the number of y-intercepts, the end behavior, the domain, and the range of the function. So the graph is a log graph, and there are some things that we need to know about the log graph. So first of all, the x-intercept, can you tell by this graph what the x-intercept is just by looking at it? Somebody shout it out if you know. Okay, the x-intercept is x equals 1, or 1 comma 0, right? It crosses the x-axis at 1. There's 2, so this has got to be 1. So the x-intercept here, right on, is 1, 0, comma 1, comma 0. That's the point, the x-intercept. And I do like you to write these as points, not just x equals 1, okay? 1, 0. All right, that's the x-intercept. Now, is there more than one x-intercept for a log function? Does it curl back around somewhere and come back down at all, or does it do that? Does anyone remember? No. No. The answer is no. It keeps going. It kind of keeps going up. It will kind of level out a little bit, but this was just a very steep graph that they're showing right now. Okay, the number of y-intercepts. How many y-intercepts are there? 0. In a regular logarithm graph, there are no y-intercepts. Okay, because when x equals 0, okay, if you were to plug that in to this graph, okay, log of 0, base, well, there's no base there, so that's base 10. Okay, let's try that on our calculator and see what we get. Oh, it looks like we did some work here. That's good. Okay, so log of 0. Let's see what that is. It's error, domain error. It does not work. So there is no value. It's undefined. Because 10 to the power of what value, right? What value will give you 0? 10 to the power of no value will give you 0. It'll never equal 0. So right, there are no x-intercepts. Okay, so the x-intercepts, there are none. Yes?
You said that you specified for a regular logarithm graph?
Yes. That's right. If the function, so if the log function, if it's like, if this x is changed inside here, like it's x plus something, 5, or minus something, then yes, there will be a y-intercept. So if the graph is like shifted over to the left or right, then yes, it will have a y-intercept. But for this graph and for a regular log x graph, there's no y-intercept. There's like a vertical, it's called an asymptote. Have you guys heard that word before? Vertical asymptote? Okay. All right, so end behavior. So remember we talked about end behavior, like where the graph starts and ends, which quadrants? So the end behavior here, what quadrant does this graph start in?
4.
So 1, 2, 3, or 4. Yeah, it starts in 4. It does not cross this y-axis boundary. So it starts in 4 and it ends in 1, right on. So 4, 2, 1. That's the end behavior. All right, the domain. So what are the possible x values for this graph as you see it here and as you understand it here? What are the possible x values? Well, we know it only exists in these two quadrants. So it doesn't exist at 0. So that's going to be like an open circle. And so the x values are all these ones over here. So the domain is only the positive x values, but not 0. So x greater than 0 looks like. Okay, just x value is greater than 0. And just a reminder, this is in your homework, so please have your homework out and check your homework. Make sure I'm doing this right, and if you haven't done it, you can just copy it while I do it here, right? Okay. All right, finally the range, okay? So the range, what are the possible y values? Is there a minimum and a maximum y value that we can see, or? No, not really. There's no minimum or maximum because it keeps going forever down and then forever upwards. It never actually levels out and gets flat. It keeps going up just slightly. So the domain, or the range here, sorry, is just y is an element of all real numbers. Okay, so it can go this direction, up and down forever. Okay, I believe that should be all the answers for number 1. Any questions about that? No? You guys are good? All right. Okay, let's take a look at number 2 then. How many of you are all done number 2 already from yesterday? Oh, 2 hands go up, really? You guys didn't get that far? You guys get 2? You did 2? Okay. We didn't do any homework yesterday? Okay. This is 7.4. I'm gonna do 2. Yeah, I'm gonna do 2. Okay. Identify which of these graphs are logarithmic functions. Okay, so we need to spot the log graphs here. So just of these 4, I don't have all of them. There's more in your textbook, but let's take a look at these 4. Does A appear to be a logarithmic function? Yes or no? Yes or no? What do you think? Okay, many of you are shaking your head no. All right, yeah, that's right. This is an exponential function, right? So we took a look at those as well in this chapter. This is an exponential function. Okay, so that's not, okay? What about, well, let's go across over to the right here. D. Does D look like a logarithmic function? Does that appear? Okay, so that does not look like to be a logarithmic function. Yeah, we have like, looks like almost a turning point here. It doesn't, not really, but this is a cubic function, right? This is like an x cubed something. So that's not a log. What about this one? This is B. Does this look like a log function? No, that's a quadratic, right? That's an x squared something with some other terms. So that is not. What about E? E is a logarithmic function, yes. Even though it's kind of flipped upside down, that's totally okay. What's happening here is this has some kind of A value that is going to be negative, okay? So the A value, you should have learned about that yesterday. You should know a little bit about A, right? We talk about A value. That's like in the first question, this is 8. The 8 is the A value. So it stretches the logarithmic values up and down. Okay, it squishes them or stretches them up. But a negative value takes the log function and it totally flips it upside down. So this would have a negative A value. That does look like a log function. It looks like there's a vertical asymptote there, okay, and it starts to bend over like this, so it curls down a bit like that. So yeah, the positive A value version would look something like this, and that clearly is a log function. Okay. Questions about 2? Yes, no? No? Okay. You guys look really tired today. You guys tired, or is this too easy? Too easy? Somebody say too easy? Okay, all right, well, sorry. I'll try and give you harder questions another day. Let's take a look at 4 together here. Number 4. So using graphing technology, you had the graphing calculators yesterday. Don't jump up and grab one if you don't have one right now, but I'll do this on the board with you. I think that possibly this one, did you guys do this one yesterday while I was gone? Let me just see. Yeah, doesn't this look to be this question, I think? You guys remember this from yesterday? Yeah, some of you. Wow, okay. Okay, so we've got the log, so here's your log button, log x, and negative log x. That's what this question is asking about. So use graphing technology to graph these 2 functions. Compare the graphs, consider the x-intercept, the number of y-intercepts, the end behavior, the domain range, and whether they're increasing or decreasing. So there's going to be a lot of similarities here. So let's just take a look at them. Okay, I will screenshot this and we'll blow it up a little bit. All right, so these are the 2 graphs here. Okay, so this one right here, this one that goes up is y equals log x, right? And this one is y equals negative log x. So all of the y values are like negatives when you multiply a negative there. Okay? So let's see, x-intercepts. What is the relationship between the x-intercepts of these two graphs? They appear to be the same. Does everybody see that? Now, if you aren't sure about that, go back to the calculator here. And the x-intercept for this, it should be, for this log one, should be 1, 0, right? The log of 0, the log of 1 equals 0. So this should be, let's just do a value here, number 1. So I'm going to plug in x equals 1. And we have 1, 0. Okay? Now on these calculators, it'll show you what function this point is on. It'll show you up there. And if you hit the cursor up or down, you can go to the very next function and see how this intercept is the exact same. So if you flip between functions, the point doesn't change. So it is indeed the same. So x-intercepts are the same. Number of y-intercepts. Okay, so y-intercepts, they are also the same. They're both 0, right? 0 intercepts. Not y equals 0, but 0, there are none. And again, you could check that on your technology, graphing calculator, Desmos if you're at home. You can put this on Desmos, which you've seen before in class here. So again, you could do second function trace on this calculator, gets you to the calculate menu. Just hit enter for plugging in an x value. And you can plug in 0, and it'll say nothing, undefined. There's no y value. So for both graphs, you see, same thing. So there's no intercepts, or none. Okay, good. Any questions so far? You good? You good? You're all right?
Clarifying what it said.
Okay, about the y-intercepts or about the x ones?
No, just the x-intercept equals the same. Like just.
Yeah. Oh, the x-intercepts are the same value.
Yeah.
So I'll clarify that some more. 1, 0 for both. Yep. Okay. All right, good. Thank you. All right, end behavior. So for the log x, the end behavior goes from 4, quadrant 4 to 1. And then for the log is negative x, kind of goes from 1 to 4. And we usually read that as the x gets larger, right? So that one's a little different. They're the same quadrants, but for log x, it's 4 to 1. And for negative log x, it's 1 to 4. All right, so domain is the next one. Domain should be the same, right? So they're the same for domain, same domain. And that's going to be x is greater than 0. So no negatives and no 0, but everything beyond that. Do you guys understand why there's no negatives for the x? Do you guys get that? Why the graph doesn't exist over here at all? If you recall the nature of the log graph, right? It's an exponent, right? Oh, I'm gonna try and make some space here. Give me a second. It's an exponent. So, for example, log of x, base 10, okay? So we're looking for 10 to the power of something equals x. So 10 to the power of some number equals x. And if x was 0, what exponent goes in there? Well, 1 is 10. Negative 1 is 1 over 10. So that's just 0.1. 0, 10 to the 0 is equal to 1. So there actually is no number, positive, negative, or 0, anything, that actually makes this statement true. So that's why there's no 0. But if you think about x equals negative, if you change the powers of 10, this will never ever be negative either. It will only be 10 to the 10, for example, is large, and 10 to the negative 10 is very small. But these exponents, if you change them around, will never make this value, it will never make it negative. So that means there are no x values that cause any a negative y values kind of thing. Okay? So that means that this right here can never be negative. It always has to be positive. Yes?
What happens if the base of the log is an odd number?
The base can be an odd number, but the base can't be negative either. Yeah, the base is only going to be positive.
So if it's log base 3, negative 3, what would that look like?
Okay, so your question is, what does log base 3 of negative 3 equal? Like, okay.
Or just an odd number and a negative.
Okay, so log, let's say base 3, and then negative 3 is here?
Yeah.
Okay, so what does this equal? All right, so then what you want to do is you want to say 3 to the power of what equals negative 3. Okay, so what is the power that makes this statement true? Remember, you're just doing exponents. So if you tried 1, that would equal positive 3. If you tried negative 1, that would be 1 over 3. If you did 0, 3 to the 0 is just 1. So there is actually no exponent that will give you that negative 3.
Okay.
And that's kind of my point. So this is a problem if you have a negative number in there. It doesn't work. So that's why the graph doesn't go into the negative x's, because there's no graph to be graphed there. Okay, we almost done this question. Range. Okay, range is the same for both. It's YER. The big difference comes here, the increasing or decreasing. So let me just talk about that real quick. So increasing and decreasing. Obviously, the y equals log x. This one, this one right here, that's this graph right here. That y equals log x is increasing. All the values are getting larger and larger. So log x is increasing, and negative log x is coming down like this. All these values are getting lower and lower, so this is decreasing. All right? Okay. If you understand all that, that's great. If you're not excited about it, that's okay. But as long as you're understanding, because you need to be able to do this on your own. So I'm just trying to help you with that. All right. So that's 1 and 2. I think that's 1, 2, and 4. I will do 5 here too. I just want to get you to. What was the question you guys asked about? Was it 5? It was 5. Okay. So let's talk about 5 too. Which I think is the next one on your homework list anyway. So number 5, predict the x-intercept, the number of y-intercepts, end behavior, all that sort of stuff for these functions. Increasing, decreasing, all that. You can use graphing technology if you want, but try to do this before you graph it. Okay, so let's take a look at A. So f of x is the same as y. Y is a little bit easier to write, so I'll just write that. So we're rewriting this. So the A value, remember, is a stretch value, right? The A value stretches the graph. So I'm going to try and draw xy here. So the log x would kind of look something like this, right? That's kind of your typical log x shape, where this is 1, right? The 3, what that does is it stretches all of the y values times 3, right? So 0 times 3 stays 0. But this value times 3 goes up times 3. This value times 3 goes up times 3. Okay? Again, this value goes up times 3. And so when you piece these all together, it kind of looks like this. A negative 1 times 3 is negative 3. Okay, times 3. So it kind of starts to look like this. And that's where you get the stretched up version of the graph. So that's why it looks like that. So it goes kind of like this. This is going to be bad with the tablet here, freehand. From there, and then kind of like this, okay? So that's what the y equals 3 log x would kind of look like. without giving actual values there. So the x-intercepts don't change, the y-intercepts don't change, the domain doesn't change, the range doesn't change, the increasing, decreasing doesn't change. It's all the same as a y equals log x. Okay? Okay? All right, b then is -9. Okay. So what does the negative a value in front of the log, what does that do to it? That flips it this way. It flips it vertically. So if I'm going to do this one maybe in red, then it's still going to have this as an x-intercept. Okay, nothing's changing there. But then it kind of goes down very steeply and like this. Okay? So it's very, very steep. That's a bad drawing. Here, let me see if I can fix that. It goes... It's very, very steep, but still starts to curve over here like this. All right? So that each y value on the regular log function gets multiplied by -9. So this one goes down to way down here times -9. This one goes to way, way, way down here, -9. This one times -9 goes to about there. This one times -9 goes to about there, and so on. This -1 times -9 makes it a positive value. It goes up here, right? This one times -9 makes it a real big positive value. And so that's why it flips. Okay? So the only thing different for this one, everything is the same, the intercept is the same, blah, blah, blah. The only thing is that it's decreasing instead of increasing. Okay? So for B, whatever, list all your stuff. The only thing that's different is this is decreasing now. Okay, was there anyone from number 5 that you had trouble with that you want me to go over? C? Okay, so let's do C next. Okay. Now in the lesson, we talked a little bit about ln of x. Let me just pause and talk a little bit more about ln of x. Okay, this is the natural logarithm, which the natural logarithm of x really is, it's a logarithm, but the base is a special base. And it is a number, which is an irrational number, and it's signified by the letter e. Okay? Now, you don't really have to know about natural logarithms that much. What you have to know is that a natural logarithm, and this ln comes from the Latin logarithmus naturalis, whatever, and so that's why it's ln. But the natural logarithm has a base e, and this base, the reason why this was created and logarithms like this were created is because in calculus, if you ever take calculus, you will find that doing calculus methods to a natural logarithm function is far easier than doing it to another type of regular log function. Okay? So this was created to make calculus easier. And it does make calculus quite a bit easier. There are certain characteristics of the exponential, y is e to the x, and this natural logarithm, y equals ln x. It makes calculus much easier. But you won't have to worry about that if you're not going to take calculus. But it is an important, very important constant. It's like 2.718, blah, 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 blah. Something like that. So it's kind of between 2 and 3 for a base. So don't worry about this, the difference here. Just know that this is a regular logarithm, just has a base e. Okay, not a base 2, not a base 3, not a base 10, but a base e. Okay? All right, so that's all I'm going to tell you about natural logarithm. It's just a regular logarithm with a little different base. So this one is, what color should I do this one in? I can't do it in black because the background's black. Is there a color I haven't used? Hey, I'll go to the palette here. Let's see. What color do you want? Pink? Pink. Pink, pink, pink. Okay, of course. Okay, so this one, let's do this one in pink. So this is a positive a value. It's just really large. So if I can go over here a little bit, then, actually, let me move this down. Move this diagram down a bit. Okay, so this 12 ln x, this blue one is the regular ln x, right? But the 12 then is really, really steep. So it goes really steep and then still hits the same intercept, but then goes really, really, really sharp. Even steeper than the -9, if that's even possible to draw. So that's kind of what it looks like there. Okay? And again, the exact shape is determined a little bit by that base, but you don't have to worry about that. Just if we're talking about characteristics, we want to talk about domain. So domain is, the same as a regular one. So it's x greater than 0. The range is y is an element of all real numbers. Okay. The increasing, it is increasing for sure. Did I miss something? Intercept, sorry. Intercepts, so x-intercept is 1, 0, same. Y-intercept, there's none. But that's what the ln is like. It's just a slightly different base is all. Okay, but all the characteristics really are the same as a regular log. All right. Okay, so that's the first 3 for number 5. I'll let you guys do the rest, whatever, on your own. Hopefully that's a good start. Okay? All right. I can do number 8 a little bit later here. I don't want to overdo it here. Please take some time now to finish your homework for 7.4 here.